The other big name theorem that we're going to talk about in this section is the title of this section. It's the mean value theorem. It says if f is continuous on the closed interval a to b, so this is the same condition that we started with for Rolle's theorem, and differentiable on the open interval a to b, again this is another shared condition between the two, then there's at least one point c in the open interval a to b such that f of b minus f of a over b minus a is equal to f prime of c. And the reason this is the mean value theorem, this is, remember, the average rate of change, so in other words, the mean rate of change. So there is some point where the average rate of change of the endpoints is equal to the instantaneous rate of change of the function at a certain x value. So this time we only need our function to be continuous and differentiable. We don't need the endpoints to share the same y value this time. So I'm going to draw some function, perhaps it looks something like this. If I were to find the average rate of change between the endpoints, in other words, that is the slope of the secant line, what the mean value theorem says is there is at least one point c in between a to b, so maybe this is my c right here, where if you were to sketch in the slope of that tangent line, and I don't think that's quite it, I think probably right there. If you were to sketch in the slope of the tangent line at that x value, at this point c, I would have the exact same slope as this other red line. So I would essentially have two parallel lines. And again, you may have more than one. In this case, we actually have another one probably right about here. If we were to sketch in the tangent line, we would actually have a second. So this is maybe C1, and this is C2. So there is at least one point where the instantaneous rate of change, or the slope of the tangent line, is equal to the slope of the secant line between A and B. So this can lead to some really interesting problems. Here we've got an applications problem. It says Usain Bolt set a world record of 9.58 seconds in the 100-meter dash in the summer of 2009. Did his speed ever exceed 37 kilometers per hour during the race? So what we're going to do is we're actually going to use the mean value theorem here. I'm assuming that his speed, because this is describing his speed, the function of his speed is both continuous, which means that there are no, right, he wasn't running at 10 kilometers per hour and then all of a sudden jump all the way up to 20, right? It's some place he had to cross all those numbers in between. So it's continuous. And is it differentiable? Well, yes, it's a nice smooth curve. And to be honest, here I am sort of hand-waving a little bit and say, you know what, we're not going to worry too much about those conditions. I'll show other problems later where we do maybe need to worry about those. So Usain Bolt, he started at 0, and he ended up at 9.58 seconds. He had traveled 100 meters. So what I'm going to do is I'm going to look at the average rate of change between these 2 points, because essentially these are the endpoints. He started over here at 0, and he ended up at 9.58, 100. So I'm going to find the average rate of change. So in other words, I'm going to find the slope of this red line right here that I have, this guy right here. And I'm going to look at that slope, and hopefully, if it's greater than 37, there will be at least one value where we have the same slope. So we would have an instantaneous speed of greater than 37. So let's find the average rate of change here. I'm going to take, let's see, f of b. So this will be my x comma my y. So f of b, this will be 100 minus 0 divided by 9.58 minus 0. So I have 100 divided by 9.58. We want to keep our units in mind because we said meters per second. So actually, let's go ahead and get a decimal approximation. 100 meters per 9.58 seconds. He traveled about 10.44 meters per second. And I just need to quickly convert this to kilometers per hour. So I'm going to go ahead and let's convert seconds to minutes in, in 1 minute there are 60 seconds. So those two cancel, and then I need to convert minutes to hours. There are 60 minutes in 1 hour. So these two cancel. Now I'm in meters per hour, but I need to convert this to kilometers per hour. So in 1 kilometer, there are 1,000 meters. Meters cancel. Now I'm in kilometers per hour. So if I take 10.44 times 60 times another 60, divide it by 1,000. Here I have 37.584 kilometers per hour. That was his average speed on this run, on this 100-meter dash. So going back to our example here, the slope of this secant line between my start point and my end point, in other words, is 37.584, which is greater than 37 miles per hour. So because his speed function is both continuous and differentiable, there is at least one point where the instantaneous rate of change, his instantaneous speed, was also 37.584. Without a function, without an algebraic equation, there's no way for me to identify exactly when it occurred. But the mean value theorem says, well, hey, there has to be at least one point. There might even be more than one. But there's at least one point where his instantaneous velocity was greater than 37 kilometers per hour. So that's just kind of a neat application of it. I think it's kind of a neat little problem. More often we'll probably see more classical mathematical problems. So here in these problems, we're going to first of all determine whether the mean value theorem applies. And if it does, we're going to find the points that are guaranteed by the mean value theorem. First up, I've got f of x equals x cubed minus 2x squared on the interval 0 to 1. So I'm going to look at this and say, you know what? This is a polynomial. I know it's continuous. Polynomials are continuous everywhere. That's not going to be a problem. And is it differentiable? Well, yes, because the derivative of a polynomial is a polynomial. If you need to, go find the derivative for yourself just to convince yourself. So the derivative would be 3x squared minus 4x. Well, this is also a polynomial, which means it exists everywhere, which means it's differentiable everywhere. So yes, the mean value theorem applies here. So let's write that out. MVT applies, which means we've got more work to do. Now we need to go and find the point that's guaranteed by that. So the mean value theorem says f of b minus f of a over b minus a is equal to f prime of some c, some point c within that interval a to b. So first I need to find the average rate of change first. So over here I'm going to look at f of 0. Let's see, this will be 0 to the third minus 2 times 0 squared. 0 minus 0 gives me 0. And f of 1, this is 1 to the third power minus 2 times 1 squared. So this will be 1 minus 2, gives me negative 1. So if I want to find the average rate of change, f of 1 minus f of 0 all over 1 minus 0. Let's see here, f of 1, that's negative 1 minus 0 over 1 minus 0. I'll have negative 1 over positive 1 or negative 1. So I found the average rate of change, in other words, the mean rate of change. I'm going to take this negative 1 now and plug it into my mean value theorem. So negative 1 is equal to the derivative f prime of c. It doesn't matter whether you use c or x. C is just a placeholder. I'm just going to set it equal to the derivative, which we already found. Set it equal to 3x squared minus 4x minus 1. Oops, not minus 1. I don't know where that minus 1 came from. And I want to solve this equation, essentially. That's the last step here. This is a quadratic equation. It's easiest if I set this equal to 0. So let me section this off. I'm going to add 1. So 0 equals 3x squared minus 4x plus 1. Let's see. I think this should factor. 3 times 1 gives me 1. Two numbers that multiply to be 3, add to be negative 4 would be negative 3, negative 1. So I always like to do my factoring by grouping 3x squared minus 3x minus x plus 1. And let's see, I can factor out a 3x. That'll leave me with x minus 1. Over here I can factor out a negative 1. That'll leave me with x minus 1. So this is 3x minus 1 times x minus 1 is equal to 0. Take each factor now, set it equal to 0. So 0 equals 3x minus 1. 0 equals x minus 1. So 1 is equal to 3x, which means that 1/3 is equal to x, and 1 is equal to x. So, okay, we've said that the mean value theorem applies. We set up this equation, which is exactly what the mean value theorem says. Remember that the mean value theorem guarantees a point in the open interval a to b. So it has to be strictly between a and b. So that means I can't take 1 because 1 is not in the open interval. We have to be strictly in 0 to 1 open, which means 1 cannot be guaranteed by the mean value theorem. In this case, x equals 1/3. That is the only point that is guaranteed by the mean value theorem. So 1/3, and I can check 1/3. Yes, that is in between 0 and 1. That is in the open interval 0 to 1, which is what we wanted. Let's look at a couple more here. This time, I have g of x equals 2x to the 1/3, and I'll be working on the interval -8 to +8. So if I look at this g of x, I can always rewrite it 2 times the cubed root of x. So I need to think, first of all, is this function continuous? Well, yes, it is. 2 times the cubed root of x, I'll say cubed root of x. That is continuous everywhere. 2, a constant multiple of 2, that's not going to have any impact. So yeah, it's continuous everywhere. Is it differentiable? This part I'm a little bit less sure of. So I'm going to find my derivative, and let's do that over here. I'm going to find my derivative. So g prime of x is 2 times 1/3 times x to the -2/3. In other words, this is 2 over 3x to the 2/3 power. Remember, differentiable means that the derivative has to exist everywhere in the open interval, right? It needs to be differentiable on -8 to +8. Everywhere in between those two values. Not necessarily at those values, but everywhere in between. If I look at my derivative, g prime of x, which I just found, I have a rational function, or rather a root function here, I suppose, but I have this power of x in the denominator in either case. I'm going to take that, set it equal to 0 because I'm worried about it, making my derivative undefined at a certain point. So I'll solve this equation here, divide by 3. I've got x to the 2/3 is equal to 0. Raise each side to the 3/2 power. I have x equals 0. So let's think about what we just said here. Really what we were thinking about is we were thinking about places, what I really should have written is places where g prime of x does not exist. Thinking about where does the derivative not exist. That's kind of what should have gone right here. So we took the denominator, set it equal to 0, and we found, okay, well, the derivative does not exist at x equals 0. That's a big problem for us because that lies in between -8 and +8. So what that means for us is it's not differentiable on -8 to +8. Which then means that this function, or excuse me, the mean value theorem does not apply. As soon as one of these two conditions is not true, the whole theorem sort of just falls apart. We can't use it here. So, okay, cool. The mean value theorem does not apply. And at this point, that's it. I'm done with my problem. If you come across a problem where the mean value theorem does not apply, you do not need to show any more work. Let's look at one last example here. This time I have h of x equals x divided by x plus 2. I'm working on the interval -1 to +2. So let's see, we need our function to be, remember, continuous, and we need it to be differentiable. And actually, let's write it continuous on -1 to +2 and differentiable on -1 to +2 open. So I see this rational function. I'm kind of worried about the denominator. I'm going to take the denominator, set it equal to 0, x plus 2 equals 0. I end up with x equals -2, which means that my function is not continuous at x equals -2. But if I look, I only need to be continuous on -1 to +2. -2 is not in this interval. So really what that means is it's no problem. If this is the only point of discontinuity at x equals -2, then that means it must be continuous everywhere else, which means it's continuous on -1 to +2. So okay, the first part's good. Second part, differentiable. Here, this one, it would help to find the derivative. So we are going to use the quotient rule. Let's find our derivative h prime of x. Let's see, low, x plus 2, d high is 1, minus high, x, d low is 1, all over x plus 2 quantity squared. This is really x plus 2 minus x, all over x plus 2 quantity squared. This is really 2 over x plus 2 quantity squared. So this is my derivative. Where does my derivative fail to exist? Well, I'm going to have the same problem I did in the last one, or I should say same non-problem, because it will not exist if the denominator is 0. X plus 2 quantity squared, set that equal to 0, gives x plus 2 equals 0, gives me x equals -2. Again, that's not in this interval of -1 to +2. So what that means for me is, yes, it's differentiable on -1 to +2. So that's good. That means that the mean value theorem applies. We get to do more math. Yes. The mean value theorem applies. So okay, what does the mean value theorem say? The mean value theorem says there are some points where the average value, so f of b minus f of a over b minus a, the average rate of change is equal to the instantaneous rate of change. So I'm going to go ahead and find the average rate of change first, set that equal to the derivative, and then I'll have an equation which I can solve. So let's look at f of 2. f of 2, this is 2 over 2 plus 2. This is really 2 over 4. This is 1/2. f of -1, this is -1 over -1 plus 2. This is -1 over +1, gives me -1. So let's see, if I find my average rate of change, f of 2 minus f of -1, all over 2 minus -1. Let's see, f of 2, that was 1/2 minus -1, all over, that's really 2 plus 1, so all over 3. So 1/2 plus 1, I should have 3 over 2 divided by 3. I'm going to multiply by the reciprocal to get rid of that, and I end up with 1/2. That is my average rate of change. So that's this side of my equation, 1/2. I'm going to set that equal to the derivative, which I found earlier. The derivative simply said 2 over x plus 2 quantity squared. I'm going to go ahead and try to solve this equation now. So I'll multiply both sides by, let's see, x plus 2 quantity squared. Actually, let's do that in red so that we don't get mixed up. I'm going to multiply both sides by x plus 2 quantity squared, which on the right-hand side, those two terms will cancel. I'm also going to go ahead and multiply by 2, which means these two will cancel. So I should have x plus 2 quantity squared is equal to 2 times 2. This is 4. You need to take the square root, which I run into a slight issue when I do. I'll have x equals plus or minus 2 after I take the square root. Oops, not x. I will have x plus 2, excuse me. X plus 2 equals plus minus 2. So that's no problem. I just have to split this up into x plus 2 equals positive 2, and x plus 2 equals negative 2. We'll solve each equation. On the left-hand side, I'll have x equals 0, and on the right-hand side, I've got x equals negative 4. And remember, the mean value theorem says I want only points between negative 1 and positive 2. So let's check. We want to be between negative 1 and positive 2. Well, 0 is between negative 1 and positive 2. That works. However, negative 4 is not, which means it's not a point that's guaranteed by the mean value theorem. So, sorry, negative 4. So this is the last big named theorem of this section. It's a relatively short section. In the next section, 4.3, we're going to make up for it. It's a pretty long section, but it's a really, really important section. There's a lot of great stuff in that section, so we're going to spend quite a bit of time there talking about derivatives, second derivatives, probably, if I'm honest, and don't tell other sections I said this, but 4.3 is really my favorite section. So we'll take a look at that in the next video, in the next section. Get excited, guys.